So hello everyone and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. I'm Ekaterina and I would like to introduce our speaker today, Dr. Nicolas Fedorczak, who will be speaking about intermittent transport at the edge of tokamak plasmas. Dr. Fedorczak completed his master's degree in the fusion field in France in 2006. Then he became a PhD student at CEA in France, where he was working on experimental characterization of turbulent transport at the edge of tokamaks. Then he continued his career as a postdoc at UCSD in San Diego University, where he focused on the interaction between turbulence and plasma rotation. From 2012, he is a research engineer at CEA, where he is based now. His main interest is experimental physics on plasma wall interaction and power exhaust in metallic environments. During this time, he participated in various tokamak experiments, including Tore Supra, TCV, Aztec Upgrade, JET, Compass, Golem, and from 2021, he became a group leader for power and particle exhaust in the West Tokamak. So without further delay, I give the floor to Dr. Nicolas Fedorczak.
Hello, everyone, and thank you very much, Katie, for inviting me and for this nice introduction. So, as you said, I will speak about intermittent transport at the edge of tokamak plasma, and more specifically, what we mean by intermittent transport, waves or blobs, and the duality there between these two definitions. So this has been a subject for me for many years, and since my PhD, I have been working on that more or less continuously. So I'm glad to present this today. And I would like to thank first my mentors, I would say, so Philippe Gendry, Xavier Gerbet from IRFM, colleagues, Patrick Tamin, Jamie Gunn, Pascal Meunier-Gerbet, and my PhD students, and especially Mathieu Perret, who was deeply involved in the last development of these studies. So that will be the outlook of my talk. So the question here is to build a transport model for plasma boundary layer. So if you take a schematic of what is a cross-section of a tokamak reactor, for instance, you have a fusing core that produces a lot of neutrons. We will not care about neutrons. And you have alpha particles depositing thermal power to the plasma to sustain it. And this power has to be exhausted by basically two ways: radiation, but you cannot radiate everything to sustain good confinement. So you have a significant part of this thermal power for a reactor would be in a range of 100 to 300 megawatts that will be flowing through the boundary layer to an exhaust system. Okay, and the question really is to design the exhaust system for next step reactors based on the current knowledge we build from current experiments. So I will do a very naive and simplified this introduction to toroidal confinement, because it is a way to describe the problem and to make analogies between global confinement and micro instability. So then I will go to interchange instabilities, filaments, describe then some spectral approach and things we could do to push it further. So toroidal confinement is meant to confine energetic particles. So we have plasma, we want to hit at several tens of kilo electron volts. So obviously we have charged ionized particles, electrons and ions. And magnetic confinement is good to confine particle trajectories across magnetic field. We have Larmor radii for electrons and ions, which are in the range or below 1 millimeter, let's say. So if you have machine size of 1 meter or above, you have a very good confinement of the transversal direction. Now, along the magnetic field, the free thermal motion has to be confined. So what we did in tokamaks or stellarators is to close this magnetic field in a toroidal direction. So you confine third direction. But the consequence of that is that you create a magnetic field that varies across the reactor volume. And particles during the Larmor motion will experience the gradient of magnetic field. And the consequence of that is the appearance of vertical curvature drifts, which are basically more or less proportional to the particle energy and inversely proportional to the magnetic field and inversely proportional to the charge of the particle. So electrons, for instance, would move up and ions move down. So we create a charge separation, but this cannot be sustained in plasma. You cannot really separate the charge. So you start separating the charge, and then you have directly a vertical electric field appearing. And this electric field then induces radial plasma drift, E cross B drift, which is oriented outward for both electrons and ions. And so you have a deconfinement of your global plasma towards the outer midplane wall. And for a plasma of a size of 1 meter in minor radius, the ordering drift velocity with a simple toroidal magnetic field, would be in the range of a fraction of the sound speed, which is basically of very moderate efficiency because the sound speed would be the natural extension speed of a plasma which is not magnetically confined. So this would be a very low efficiency. And so you have to compensate this vertical drift from the curvature. So the way we did that in toroidal devices is to add a poloidal magnetic field in a way that you short circuit or you connect magnetically, connect the bottom and the top of the device so that electrons drifting up and ions drifting down are allowed to flow along helical field lines and short circuit this charge separation. And it works really well. Tokamaks, you do it in Tokamak by inducing a plasma current along the toroidal direction or sustain it with radio frequency waves so that you create this poloidal magnetic field from the current flowing in the plasma. In stellarators, it's more complicated. You do it with external coils, you make this complicated helical coil structure, but it's basically the same physics. Of course, different shape, different problems, but at the end, you get a fusion-compatible energy confinement in the device. So it's really good for fusion. Now comes the second problem with this configuration that you have plasma is organized as concentric layers, so flux surfaces which are concentric. So the core flux surfaces are said to be closed, so that the magnetic field closes on itself. When you move closer to the wall, whatever is your magnetic configuration, you end up with field lines connected to the wall, called boundary plasma or scraper layer plasma. And in these regions, field lines are connected to the wall. And all the power you put in your plasma escapes radially, enters this boundary plasma layer, and flows to the target or to the wall. And this is where the power is deposited. Now, just simple physical ordering, the free parallel motion along this field line takes about 1 millisecond. So every particle crossing separatrix would take about 1 millisecond to go to the wall, and there it is absorbed. So plasma doesn't have much time to extend radially. So this boundary plasma is very thin radially. It's in the range of a few millimeters. And so at the end, the wetted area you would get here, so the red stripes, is overall in the range of 1 square meter, which is very tiny. And if we extrapolate this 1 square meter to a reactor from scaling laws, this is pessimistic, but this is what scaling laws give, you still have to exhaust 100 megawatts. So it makes about 100 megawatt per square meter, which you cannot handle with technologies. And so the first right question is, can we trust these experimental scaling laws, and how can we scale current observations to reactor sizes? So for this, you need a model for describing the transport in this boundary plasma. So I brief recall, so toroidal confinement gives access to compatible confinement performances for fusion, but the other side, you have very concentrated plasma wall interaction. And this is what is, let's say, the subject of this topic. How can we describes the transversal size or the size of the weighted area for the plasma interaction. And there comes transport physics. Okay. Now, if you look with adequate diagnostics to what happens at the frontier of the plasma between the core and the scrape-off layer, what you see most of the time is active turbulence. Okay, so this is a video taken from Tore Supra using fast visible imaging. Resolution is not very good. The time dynamics is not very good, neither. This is still 50 kilohertz. But what you see after some treatment of the image is a fluctuation of plasma density. And you see that it takes the form of elongated filaments moving toroidally because we have large scale flows. And you see these bursts going outward. And this is what we call plasma filaments. You see they come intermittently, they are localized in space. And then you could think, okay, what is the mechanism behind this? And this is the nice analogy I always do with Tokamak confinement, is that remember this picture of having charge separation on the global scale of the machine. Well, you could redo exactly the same demonstration for a small scale density filaments, where electrons would move up of the filament, ions down of the filament. So you have vertical electric field appearing inside the filaments that would move it outward. And this is exactly the mechanism that makes these filaments moving out across the separatrix. And so this is what I call generally interchange, because like analogy with gravity, you have dense plasma that moves toward more diluted region along the gravity field. Okay, and this is in fact a very basic curvature generated mechanism that is underlying most of the turbulent instabilities in Tokamaks. So it's this is a very, of course, simplified picture for most of the turbulent instabilities, but this is still something to understand what's going on. So now if you look closer with other diagnostics, like with longer probes, you could gain much more quantitative measurements. So here I illustrate with measurements, again, taken from Tore Supra with a reciprocating longer probe. And I show here the profile of saturation current measured by the probe moving from the wall to the separatrix. This corresponds to the horizontal axis there. You see this exponential profile from the wall to the separatrix. This is because particles, when they cross separatrix, they are continuously lost to the target along the field line while they propagate, and you end up with decaying exponential profile. If you zoom on the time trace, you find that the fluctuations are, they extend very far to positive values. We call this skewed fluctuations. So you see the standard deviation, which is in the range of, I don't know, 30%, so quite high, but you see these large bursts for positive values. And if you zoom even more, you see that these fluctuations are in fact composed of some coherent bursts, coherent events that come intermittently. So they're not very, they're not coming with constant frequency. And this is what considered to be a signature of a blob. So one of these filaments passing through the probe. So you have this signature on the current connection. So now we would like to describe this, to have a model for these filaments, try to understand what they are, if we can scale them for reactors. So for this, we need to I will here discuss very simple models. So the minimal model you need to describe a filament. The idea here is to describe what's going on along a flux tube. If you have a overdense filament, you have this charge separation, so a vertical current, or we could call polarization current, that develops due to curvature drifts. And this current will create vortices around, and these vortices will lose charges through parallel currents up to the limiter. In that case, I'm really concentrating on a model for plasma boundary where field lines intersect the wall. Okay, so at the sheath, you have some sheath physics that induce some resistivity, so that limits these parallel losses. And so the balance of the two will give you the property of the filament in terms of speed. Okay. Now this current balance, you can turn it into what we call a vorticity conservation equation. So the vorticity here will be simply the Laplacian of the electrostatic potential. So you have a total time derivative of the vorticity that is limited by parallel losses. That would be this term. Sigma parallel is the parallel loss rate. And you have here let's say the curvature drive of the polarization from G. G would be like gravity, but it's linked to the gradient of the magnetic field. And so it is generated by the gradient of the pressure perturbation. And the pressure perturbation there is, or the pressure field, let's say, is dictated by parallel losses. So again, here, parallel loss rate to the sheath and the source term, if you want to drive the system with a source. So if you solve these two equations in a 2D plane, transversal to the magnetic field, you obtain such pattern of fluctuation. So you have a source term here, narrow, and you see that in the good, I would say in the favorable curvature region, you have this turbulence that develops to spread the source and creates a gradient of matter. And you have this nice filament sort of structure. So you have to imagine they are elongated along the field line. You just see here a cross section that takes complex shapes and so on. So this was obtained with Tokamak 2D. And so that will be, let's say, the baseline of the studies I propose on these filaments, using these nonlinear simulations to understand what they are. So, of course, when you look at these patterns, the filaments seem to be complex structures with mushroom shapes. So you have here density event. If you look at the potential event or potential map associated to this mushroom-like structure, you can recognize two vortices that would make this mushroom to move from left to right on the picture. But these are a bit complex to understand, to make simplified model. What we would like is to describe these complex structures as simplified ones. I would assume, for instance, that pressure perturbation is a simple cycle like this with simple vortices around. Because the idea here is that if I have simple objects like this, simply characterized by an amplitude and a width, I could enter these, let's say, properties in the vorticity conservation equation, simplify the different terms, and balance the source term, which is curvature, and the sink terms, which are parallel losses and inertia. Here, inertia, you have to understand it as a limiting term in a sense that if the density perturbation moves to the right, for instance, because you have created vortices, then the source of vorticity has moved as well. So you need to regenerate the vortices as a new position of the density. So this is what I call inertia. This is this term there. And so if you do this ordering, you end up with a simple expression of the blob radial velocity, function of the size, function of the different parameters that are curvature, parallel losses, amplitude of the blob. And you can then plot, for instance, the velocity of the blob, function of the size, or the inverse size. In that case, here, this is a wavelength. So you have a sheath limited regime where the curvature polarization is simply limited by the parallel losses. And you have another asymptotic regime where the source is simply limited by the inertia. And the result of the two is this red line. Okay, so this is a simple model. Question is how to apply it to simulations to validate such a simple approach, because we have complex blobs here, so we cannot simply apply this. So, interesting step is then to build average blobs to see if these complex shapes associated to individual blobs simply smear out, sort of when you overlap them. So to do that, you can take a time trace of the density at a reference point. So you have these very intermittent fluctuations with peaks. And we could say, okay, consider an amplitude interval, quite narrow, and just identify local maxima in this amplitude interval. This would define an ensemble of events or blobs having all the same amplitude at this reference position. And let's average the maps over these discrete times. Okay. And what you get is actually this very simplified picture. This is a direct, let's say, averaging of these complex maps. After this process, you get these very nice rounded blobs with very nice vortices. And so you could directly try to apply the model to them. And this is very nice. Now you have to realize this is a sort of projection here. You project, or you construct a projection of the blob patterns on selected events, selected from their amplitudes. And so it's incomplete in a sense that you cannot reconstruct from the average blobs. You cannot reconstruct the actual fluctuation map. Okay, it's not like a Fourier transform or you use a projection on a different space, but this is bijective. In that case, this is not bijective. It's just a way to construct average simplified events, let's say. So when you have these simplified events, then you can really compare model predictions with the velocity of this average blob. So this is shown in that case with a single simulation of Tokamak 2D, where I show in the horizontal axis average blob velocity found in the simulation in percentage of the sound speed. And vertical axis is a prediction of the model. You construct from the amplitude and the size of the blobs. And you see overall there is a quite good agreement. It's of course for the small blobs, I mean, or weak blobs, you would see here, this blob amplitude is quite small, 10% of the background. Model over predicts the blob speed, but as you increase the speed because you have larger blobs, larger amplitudes, agreement becomes very correct. And the trend you see is also very good. So I think it's a good proof that yes, this isolated average blob model can be verified, okay, from nonlinear simulations of the same equations, same ruling equations. So something also interesting in these average blobs constructed from the nonlinear simulation is that you find that most of them lie in this transition point between schist limited regime and inertia regime, meaning that every blob has in fact its maximum velocity. So it's just a way to set that nature, let's say, develops these filaments to be the most effective as possible to transport the source away. So then, okay, this is a verification sort of the model. Now we would like to validate it against experimental data. So something that can be done is to test them on simple simple reactors, I would say. So here I will discuss data that were collected in the Tokamak. It's not really the Tokamak. It's a toroidal machine. There is only a toroidal field. You can add a vertical field as well, but there is no plasma. There is no current induced. So you don't have this exactly this complex helical geometry you have in Tokamak stellarators. But still you have blobs appearing from interchange, because you still have the toroidal curvature. So the toroidal field is quite low. It's 0.1 Tesla, about major radius is 1 meter. And in this works, the experimentalists have used linear probes to construct 3 average blobs using these linear probes from 3 different experimental conditions. Okay. So you would say 3 blobs is not a lot, but I think it's already good to try the model from applying the model to different experimental conditions. And you see here a comparison of the average velocity, or velocity of these average blobs measured in topics versus the model prediction. You have here like blurred spots because I performed the sensitivity analysis from the uncertainties given in experiment. So you have here some uncertainty estimates. And you see overall that the trend and the prediction are really good. I mean, within 25%. It's not perfect, but considering experimental error bars and this very simple model we are using here, this is quite encouraging that the model is indeed able to describe what's going on in reality. And then we move to, let's say, more realistic conditions for Tokamak reactors. This is, I would describe here, comparison of the model to experimental data I collected on Tore Supra using a reciprocating Lange probe located at the top, equipped with an array of small collectors that you could polarize, for instance, to measure saturation current and so give electron density fluctuation, or let them float so that you measure electric field fluctuations. Again, we have constructed a very large database. We have about more than 100 plunges of the probe, scanning different plasma conditions. We identified about a fraction of million blobs on the time traces, and we constructed about less than 10,000 average blobs. So it's a lot. And you see here a comparison of the radial drift velocity of these average blobs, horizontal axis, versus the model prediction vertical axis. And because we have a lot of blobs, I don't see individual points. Here I see a concentration map of the points. So the color bar here denotes the concentration point. So you see, overall, we have some, let's say, finite dispersion around unity, but note that all the points organize around unity. And we have, in fact, overall statistical match between measurement and model. So this is very encouraging, showing that, yes, indeed, we can explain the dynamics of blobs in experiment from these very simple ordering models for isolated and simple structures. So this is very nice. But then the question is, okay, I have a model for blob dynamics, meaning that if I know the amplitude and the size of the blob, I can predict at which size it moves radially. But then what's the purpose of such a model? At the end, what we want is a model for the flux, meaning I have a source. I want to know how wide is the profile that turbulence creates from the source, because this will be ruling the heat load footprint area on the dialectal, for instance. So for this, you need to average a flux over many blobs. Okay, so a way to do this average is to consider that a blob has a certain amplitude, it has a certain velocity. So this is an instantaneous flux from one blob, but then the blob comes intermittently. So it has a certain duration, tau b, tau blob, and it comes with certain frequency, f blob. And so you can write this expression for the flux. And then you realize that if you want to build a flux model, you need a model for the blob amplitude, which distribution is statistically created. I mean, you have to define statistical distributions for the blob amplitude. You have the blob size also appearing in the model for velocity, and then you need a model for the blob intermittency. So you can think that the product of the blob duration times the frequency is what we call the duty cycle of the blobs. Okay, so you need the model for this duty cycle intermittency. So this can be somehow managed from theoretical consideration, but the one concerning amplitude and space and size distribution, for now it has been out of scope of any model. We are not able to build a model for the statistical observables. So there are people, you can find very interesting works. For instance, Garcia from 10 years ago tried to discuss these statistical observables, how you can then construct observables for transports of fluctuation level, profile decay lengths, fluxes, these sort of things. But the input statistical functions for this blob are still missing. Okay, you can just make guess and you don't know if they are right and how they scale to reactors or to different conditions. So at some point I decided, okay, maybe we could change the way we describe this transport. Blobs are fine, it's a very interesting manifestation of turbulence. We see them with camera, we see them with probes and so on, but it's then still difficult to make a link with fluxes and profile. So I thought, okay, still this is turbulence, so we think of it as blobs. Why not also thinking them as waves? Okay, because you could see here wave patterns. There is no points of things. So I will now move to this wave description. So just let me recap what I said about interchange filaments. So these are intermittent structures. We can clearly see them at the edge because we have adequate diagnostics to see them. I said that we could rule simple models to describe their dynamics, and they work quite well against experimental data. So again, average events, let's say. But still, we are lacking some statistical laws to have a complete transport model. So now let's see what we can get from a different approach. So here, I'm starting again from the same equations, exactly the same problem. Here a Tokamak 2D snapshot of the density fluctuations that are created from these two equations. And now I just looked at the toroidal spectra of density and potential, or density and radial velocity, the same. So I take here a vertical line, okay, I construct a toroidal Fourier transform, and I plot this Fourier spectra here. So these are these gray, black curves, okay. Now, one thing we found when we looked at the spectra is that density and velocity fluctuations are in phase, which means that, yes, you are in the maximum flux regime, and this phase is very close to zero for density and velocity. It's not fluctuating much. It's quite constant around zero, which is a good point. Okay, so we are always in the maximum flux conditions for fluctuations of potential and velocity. And something striking we found as well is that when you look at the spectra and you look at the time dynamic of the spectra, they weakly vary in time. I mean, the dashed line here gives the envelope of the temporal fluctuation of the spectra. And you see it's very small. Spectra are constant in time, which was striking because I thought if we have intermittency, it means that sometimes we have blobs, most of the time we don't have blobs. And so I would expect the spectra to fluctuate a lot. But then you have to think it as a statistics. If you make a very large simulation box, you will have a lot of blobs, even if they're intermittent. So you will always have blobs on your toroidal domain. But then, well, this is the question that we could discuss is what is really intermittency of these blobs? Is it just some random interference of wave patterns that makes this blob appearing? Because you still have this constant spectra to keep in mind. Okay, so if we have a constant spectra in time, it means that probably we can rule out a model for time average spectra. And if we manage to do that, if you have access to toroidal spectra, you have access to everything, in fact, as we'll explain later. So now let's think what are the first approximations we could do to describe this spectra. So the density one, you see it's decaying with a wave number. And well, if you take the density equation and you simplify it, you come to what we call mixing lengths, meaning that the density spectra is inversely proportional to the product of the density decay lengths, lambda, and the wave number k. And this is shown here at the dashed line. You see that it's in fact showing a very striking agreement against the simulation, both in shape and amplitude. There was no adjustment except for low k. You see the mixing length is diverging at low k because it is inversely proportional to k, so it doesn't do the job at low k. It cannot do the good jobs there. And for the velocity, we said, okay, let's just apply the isolated filament model. We have the amplitude from the density spectra, and we have the, let's say, the dependence with the k vector, as explained already before. And you see, again, very strikingly, is that this blob model does a very good job predicting the amplitude. There is no adjustment again. This is a one-to-one comparison. So in amplitude and shape. Shape is not very good there at high k. So maybe there are some work to do here. But still, if you think about it, now there comes a mathematical problem in this application of the blob model. It concerns the nonlinear term, the inertia, which is a product of the velocity times the divergence of the vorticity. Or not exactly this, but this is a nonlinear term. And if you do this product in a Fourier domain, this product, if you take it on the product of the mod k, then it moves to wave coupling and gives mod at 2k or 0. So there is no way they can simply apply this to the mod k. It's not working. Okay, you have to find another trick to describe inertia there. Simply. So the first thing we thought is, okay, let's think this inertia term differently. Okay, we have here, we see from the spectra that the vorticity is concentrated around a dominant wave number that we call K0, for instance. So these modes are moving fast and they are intense. You see it from the density. So this would correspond to this main scale you see. I mean, all these blobs have basically sort of the same scale. Okay, so this is K0. So these blobs, or this mode, in fact, moves across the box faster than the other mode. And you could think it as a way to disperse the energy of the other mode. Okay, so consider it as two-wave interaction or wave coupling. The dominant mode could be considered as a sort of effective viscosity for the other modes. And so this inertia term, in a sense, you could replace it with an effective viscosity term, okay, where the effective viscosity will be simply the amplitude of the potential of the dominant mode. And with a sort of similar reasoning, you could think that saturation at small wave numbers is in fact due to the same interaction with the dominant mode. And well, so this is a bit heuristic, but you could in fact modify the mixing lengths to include a saturation for small wave numbers. And when you do that, in fact, you find a very good agreement again with spectra you find in the simulation. So here's this new, we call it spectral filament model, so including viscosity and saturation, modified mixing lengths, gives this blue dashed line. Okay, you see it's there is a very good match with the spectra for potential, and spectra for density is also very well matched. Still not much for the very low wave number part, but you have to think now that this very low part of the spectrum has a very moderate contribution to the overall turbulent energy. So consequences on flux estimate or fluctuation level estimate and other transport observables, all this is weakly impacted by this small difference there. So at the end, I mean, for those who are interested, you come up with very simple expressions of the spectra for potential and density, where all control parameters appear as a multiplication factor and the spectra as a complete normalized shape, okay, which is very good then when you want to use the spectra to construct any fluid moment you could construct from toroidal spectra. So from this, you can construct analytical expressions for density fluctuation, correlation lengths, radial flux, and then everything you can derive from radial flux. And so the first thing we have to do is to verify the model against to come to the simulation. So we did a database of simulations, nonlinear simulations, flux-driven simulations, and we measured different transport observables on these simulations, and we directly applied the model, okay, without any tuning. You have here a comparison of the dominant wave number found in the simulation predicted by the model, and you see a very good agreement. The same for the amplitude of the dominant mode, both density and potential. We have astonishing good agreement The same then for fluctuation levels normalized to the background. And now, because Tokamak 2D is a scrape of layer model with parallel losses to the wall, you can also calculate the radial decay length of the profile for lambda. And again, we could compare this decay length measured in simulation to the direct prediction of the model. And again, it's astonishing how good it is. Okay, and at that point, I was really astonished that we could build a model, very simple one, sort of, that is able to describe this nonlinear simulations so well. Okay, so of course, these simulations are very simple. They are 2D, they are isothermal, but still you have complex pattern of turbulence. And in fact, you are able at the end to have a microscopic description of the fluctuations with this spectral model. So then again comes the validation step. So we perform a stage of validation against stage K, stellarator data. So you have here a top schematic of the machine. So this is a certain stellarator type. Okay. So you have here the structure of the magnetic field inside. This is a shape changes continuously around with a certain period. And the nice thing with this stellarator is that it is equipped with arrays of long probes that match the shape of the plasma locally. Okay. And with this, you can build toroidal spectra and compare to the model directly. This was very interesting. So here I want to thank the JK team, Mirko Ramish, for providing this data. This is very nice. And so you have here a comparison of the model compared to experimental data for the potential fluctuations. So the black and gray are experimental spectra, and you see the green or red are predictions from either isolated filament models that we should not use in principle, and the spectral filament model. And you see for the density here, this is only the spectral filament model. Well, overall, what you see is that, of course, the match is not perfect, is less accurate than in simulations, but still, we were astonished to find that the prediction of the model, you get the right amplitude for the spectra, at least on the dominant wave number, and the shape is more or less okay. So I think we were really happy to see that, at least for the dominant mode, we do a good job in predicting the position and the amplitude of the dominant mode, at least. Well, then we went to validation against Tore Supra data, again, using this reciprocating probe with an array of small collectors. So I use the same database as I presented for the isolated blobs, but now I looked at fluctuation or transport observables. So for instance, fluctuation level of density, of potential, the toroidal wave number of the fluctuation you can infer along this array, and the overall density decay length you find in scrape of layer. Okay. And well, you see, so we have a lot of data points here. We have about, okay, so this database is reduced to 33 reciprocations. We have about 600 time samples of 5 milliseconds over which we perform these statistical markers. Well, what you see here is that the fluctuation level is more or less well recovered, at least statistically. You see that the variation across different conditions is not well captured by the model, but at least you get almost a one-to-one comparison within 20%, let's say. And the same for potential fluctuation level. We have much of the points lying within 20% agreement between the model and the experimental points. Also for the toroidal correlation lengths, it's not perfect. You have more spreading or more discrepancy, but still most of the points lie in the right agreement region. And something that we found really impressive is the capability of the model to predict the density decay length, because this is really what we want to have, right? Is a prediction of the scrape of layer widths to predict plasma wall interaction. Of course, this is on density then, but then you can extend it to heat loads, okay? so this is what we did then, considering another database we built on Tore Supra. So we basically limited the plasma on the high field side, as you would get in ITER, for instance, when you have to ramp up the current at the beginning of the shot. This would take, I don't know, 100 seconds or several tens of seconds, where the plasma lies on the high field side of the chamber, and you increase the current slowly, and then you form the X point. And you still have concerns that you could damage the wall if the scrape-off layer is too thin in these phases. So we did a broad database from Tore Supra, scanning current, density, magnetic field, and we collected the value of the heat load widths, so lambda Q. And then we compared it directly to the model. Now, you have to keep in mind that the model uses very microscopic engineering parameters for lambda Q. We use magnetic field, major radius, minor radius, plasma current, input power. So these are the global engineering parameters we give to the model to predict the data. And you see here a very good agreement for Tore Supra cases. I mean, within 20%, you get the right tendency. And then we compared it to predictions made for ITER at three scenarios, let's say, three currents. And these predictions were made using a massive multi-machine database on lambda Q. So you have more than 10 machines, you have 1,000 data points in this database. And so from it, you can build scaling laws with a certain error bars from the dispersion of the scaling law. And we compared it again to the model. And you see that overall, the model again is able to reproduce predictions from the scaling law within 20%. So, well, it's not a proof that the model will work for ITER, but it's proof at least that the model is consistent with this multi-machine scaling. Well, so this was for a very simple geometry. Okay, circular plasma limited on the inner wall. It is easy in that case to consider that the approximations we did on the model concerning geometry are correct, because simple geometry. And we thought, okay, what happens when you move to X-point machine? Okay, X-point scenario, diverted scenario, with higher power, a lot of power. So you go into H mode, you have a very thin lambda Q, okay? And concerning this, you have a very interesting multi-machine databases where they show the evolution of this lambda Q measured in experiment function of different plasma quantities. And the most striking relation is the one linking this lambda Q, so heat flux width, to toroidal magnetic field. And this gives a very pessimistic prediction for ITER. ITER would be around 1.2 of toroidal magnetic field, and so you predict less than a millimeter for the heat load widths at the midplane. This is very pessimistic. It basically gives less than 1 square meter for the heat load area in the divertor. So we tried to apply the model, having in mind that the model is not meant to describe H mode, okay, where you have shear layers and other stuff, and you have also an X point that the model is not embedding. So, but we tried just to study the sensitivity. And so I didn't have access to all these data points, so I made a synthetic database of points using the experimental correlations in this database. Okay, and so I reconstructed these points. So you see, first of all, that this amplitude is not the same at all. I predict something like 5 millimeters there, whereas the model data give you 1 millimeter. So there is a factor of several units discrepancy on the absolute amplitude, but this is fine. This is probably this is fine. This is something we have to keep in mind. But overall, look at the shape. The shape is quite interesting because I overplotted on this model prediction the trend found in experiment, and it's basically giving the same trend. Okay, except that ITER and demo I do, let's say, more optimistic predictions. And well, this is something to keep in mind. Like, can we really trust these experimental scaling laws? Are there any hidden correlations that are not well covered by the experimental database? So we are making biased predictions for ITER. Things to keep in mind. So come back to the outline. So I described the spectral filament model to try to move away from the blob and try to say more things about fluxes. So we adapted this model from isolated filaments. And overall, it works quite well. We could verify it against simulations. We could validate it against experiments. And we have now predictions of a variety of different observables. So which is very interesting for thinking how to build experimental data to compare to codes, right? So now let's see how we could push this spectral filament a bit further. Now let's look at what 3D simulations say about transport. Okay, so here we'll discuss results obtained with the Tokamak 3X code. So we think it as an extension of the Tokamak 2D in realistic geometry. So here these are isothermal simulations, meaning that the code only simulates density and potential fluctuations in 3D realistic geometry. It's very complex, very demanding. So you have here a snapshot of the cross-section of density fluctuations. So you could recognize like filament patterns. Again, you see that a lot of stuff are going on around the X point. Shaping, distortion, dissipation of blobs that the model is not absolutely not considering yet. Okay, the simple spectral model. So what you see here, interestingly, is that I mean you could run the simulation in circular geometry. So you would get then a case which is very close to experiments in Tore Supra and close to the assumption of the model. In that case, you can measure a certain extent of the scrape-off layer. So in that case, this is about 70 Larmor radii. I should point out that the spectral model predicts something in the range of 80 in that case. So it's very not far, meaning that there is again a good agreement between the spectral filament model prediction and these 3D simulations. And interestingly, if you switch the geometry to circular limiter to diverted shape, you have a very strong reduction of the scrape-off layer width in the simulation. You basically reduce it by a factor of 6 to 7. It's a lot, right? And this is the reason why there is still under investigation. It's probably linked to dissipative effects around the X point and flow shearing effects, because maybe flows are more important in these diverted configurations and circular configurations. So at least we see that, yes, there is a scale difference when you go from limiter to diverter. We also see it from experiments. And the question now is how to embed these effects in the simplified model. Still ongoing process, I would say. So now concerning the impact of flow shear. Okay, so this is something we were very much interested because we wanted to try to link the model to transport barrier formation in the H-mode physics. Okay. And so you could run, in fact, a simulation imposing a background shear flow. Okay. So in the equation, it would simply mean to add a recall term for the potential through shear physics. Okay, you could simply say you bias the wall, so you impose a potential at the wall. So you could impose a profile for the potential, and so you have a natural background shear appearing in the simulation. And you see what you see then is that having a shear, so illustrated by the direction of these arrows for the flow, tilts the structures, the blobs. You see, blobs are not simply moving radially; they move in the transversal direction because they are tilted by the shear flow. So imagine that without shear, a blob is a simple ellipsoid moving radially outward. If you impose a shear, you will distort the shape of the filament. It will now move along tilted direction. And so we ruled out a model for this tilt because this tilt is very important for several reasons. Okay, and so we said, okay, the tilt is continuously provided by the shear flow, but you need a recall force to get a steady state tilt, and this recall force is in fact an intrinsic phenomenon of interchange, because interchange create modes oriented along the curvature, so oriented along the horizontal direction. So the shear tries to tilt the mode, but the interchange record it. And so at the end, you get a resulting average tilt, constant tilt. And while this is from a simple 2D simulation, I want to say that this is also very similar to what is observed in gyrokinetic simulations, which is state of the art of the turbulent description. So we compared the tilt measured in the simulation. So the tilt here is a simple ratio of radial wave number over toroidal wave number. And we compared it to the model. And well, we have a very good agreement. So the model, simple model we have for the recall force of interchange and the overall tilt is in fact doing a very great job. And so you could then include this tilt in the spectral model, and this will, let's say, impact the overall mode amplitudes, because if you tilt the mode, you have to see it as spreading the available energy over more wavelengths. So you overall lowers energy for each wavelength. And second, but even I think more important, is that you make a Reynolds stress, meaning that tilting the mode is a way to couple fluctuation vorticity to the large scale flow vorticity. And so you can generate the large scale flow from turbulence when you tilt the mode. And so with a spectral model, then you can embed this tilting effect and rule out new expressions for all the different fluxes, including Reynolds stress. I'm not going to describe this, but it's basically an extension of the previous analytical expressions. So again, you can rule out, you can take out of the spectral expressions the dominant control parameters, and you have a normalized shape for the spectra, which contains a shearing parameter, sort of. And you have to see it as a third regime. Okay, so you have the shear limited regime, the turbulent viscosity regime, okay, equivalent to the inner shear one. That was the non-sheared description. And then the shear flow will also impose a third asymptotic limit. That would be very far away if you have no shear, and that goes down as the shear increases, and this will modify the amplitude and the shape of the potential around the dominant wave number. Okay. So I described here, so the way we introduce, let's say, the impact of electrostatic shear flow on turbulence and interaction of the two through the Reynolds stress. There is also something else concerning the shape of the mode. Okay, it's the magnetic structure of the confinement configuration. So you have here a simple cartoon of the shape of a flux tube generated at the midplane. Okay, so this is let's say an ideal magnetic configuration for a tokamak with an export. Okay, so imagine interchange is excited at the outer midplane. This is where curvature is the most efficient. So you will start generate a plasma filament there, which is a sort of circular. And just imagine you follow the flux tube of this filament. And I just represent here the cross section of this flux tube. And you see how the shape changes when you move around. This is due to magnetic shear. So meaning that the helicity of the field lines are different when you move radially. So from one side of the blob to another one, to the other side, the helicity has changed. And so you create this sheared shape. Okay. And you see that the shape is different when you move up and you move down. Now, thinking of wave numbers, it means that you have created a negative radial wave number at the bottom and a positive wave number at the bottom. And so if you average over a flux surface, it's possible that you have a residual tilt appearing from this magnetic structure. Okay. You could see from experiment, you can see from experiments that locally, yes, fluctuations are tilted qualitatively as shown by this picture. Okay. And so now if you make this average and you include this in the model, you will have a residual tilt of the model, and this gives rise to generation of flow. And you could even see that from the model that if you switch the X point position, you will modify differently the flow. And this is what we find in experiments as well. And then you could think, okay, but what's really going on there around the X point? Are we really well describing how filaments are mitigated around the X point? So the answer is not yet. So we are partially answering the question. We are moving on these directions, and I think we have all the pieces now to implement this and study the presence of an X point on transport. So transport of particle, transport of heat, and transport of momentum as well. And especially I have in mind also, what can we say about negative triangularity? So if you could move this X point radially with respect to the plasma, how would that change the flux properties? This is something very interesting currently, and something we try to move on. So now I come to my conclusion. I hope I was not too long. So as I said, I recall toroidal curvature gives interchain instability like Taylor. Interchain transport at the plasma boundary manifests by intermittent blobs, and we can predict the overall fluxes by sort of simple spectral model. Okay, and this rose a question to me like, okay, but how do we make the link between blobs and waves? This is still, I think, sort of open question for discussion. And so I must say, on one hand, this is a very fascinating theoretical problem, okay, linked to turbulence and how we describe turbulence, but it's also of very great interest for practical reasons for fusion. Okay, we want to predict conditions of power exhaust, confinement. The fact that you have this fluctuation impacts radio frequency wave propagations and so on. So you have a lot of different subjects linked to this edge turbulence we have in Tokamak. So I'm there. Thank you. I finished. It was a bit long, sorry.
Thank you very much for a very clear and detailed presentation. A question from Guido van Oost. Please go ahead.
Do you hear me, Nicolas?
Yes, hello Guido.
Yeah, good to hear you. It's a long time ago. I have a simple question. How does the picture look in spherical tokamaks and in tokamaks with high magnetic field?
That's a good question. Frankly, we haven't tried to push this to high magnetic field tokamaks. I mean, for the spherical tokamak, I can at least bring a partial answer. It's on this application of the model for the decay lengths. You see here, I have made predictions for MAST and NSTX, which are spherical machines. And you see overall, I mean, the model gives sort of the right trend when you put together spherical machine and conventional tokamaks, and even high field tokamak like CMOD. So overall, I think there is no like showstopper in applying the model to these conditions.
Thank you.
I have one question myself. From what I've heard, it's possible to detect blobs movement also by fast visible camera or by Doppler refractometry. So I was wondering if you have experience with comparing your model with other diagnostics.
Good question, yes. I mean, we spend a lot of time working on probe data because probe gives you quantitative measurements locally. You can really quantify fluctuation of current and potential. So you have to interpret them, of course, but at least you have quantitative measure locally. With camera, it's so the movie I showed you. I took it during my PhD. Yes, this is it's quite difficult to work quantitatively with such movies because first the resolution is not very good, and you have a lot of noise, and you see you have to deal with the fact that you have a tangential view, and so you see the toroidal shape of the filaments. And so it's difficult then to disentangle transversal dynamics or transversal shape to the parallel shape. So it makes this quantitative analysis for me difficult with the camera. But I'm pretty sure that you can do very good things with, let's say, beam emission spectroscopy, where you could localize the information, Doppler, reflectometry, and reflectometry. Probably you could do this. Also, I mean, the link between blobs and reflectometry for me is still something difficult to understand. But
I see. Thank you very much.